Thank you very much for the invitation. It's my pleasure to be here and have the opportunity to talk. My collaborator, Chris, is also here. And I hope if I make a mistake, he'll jump to the rescue. Some years ago, the tradition started in Oberwolfach, at least in the Toric community, to draw the pictures of the collaborators. These are the collaborators: A for Anna Botero, B for Boris Sevlichovsky, and C for Chris, ABC. Chris, when we were working on this stuff, used to have a beard, so he doesn't have now. There is a lot of recent work in the recent years, work on toric vector bundles. Toric just means a torus equivariant vector bundle over a toric variety, extending the classical theory of line bundles over toric varieties. But it started, but I'll just mention 3 works on which most of the what I'm talking about can be found in these papers. The last 2 are ours, and they are on archive. We can find it on archive, not yet published in the journal. The first one is the classic work of Kliachko. It's a great paper with very dense, lots of interesting, important facts. I think he could have, another person may have just, instead of publishing 1 paper, deep paper like that, would have published 5 papers out of the results and material in this. It's called Equivariant Bundles and Toral Varieties, a translation from Russian. Toral means toric, which he introduced one of the first classification of vector bundles over toric varieties. It Chris, we made and realized there is connections, hopefully will be followed up by other researchers, connections to valuations and tropical geometry. I'll not mention tropical geometry in this talk, and also by understanding connection with valuation, as well as theory of buildings from buildings of algebraic groups, and which is a huge literature by itself. Work of Bruhat-Tits and then Bruhat-Tits. We understood there is some connection with that, and then it led us to naturally give extend Kliachko's classification to vector bundles over toric varieties over a DVR, but in this case, usually they are called toric schemes, which can be thought of as an infinitesimal 1-parameter degeneration of a toric variety. And this, I hope, just give you a glance of this stuff. So sigma, as usual, denotes a fan in the co-character lattice of a torus T. When I talk about toric varieties, I usually think of over C complex numbers, but the theory and all this discussion works over any field. And then toric schemes are over a discrete valuation ring, which I usually think to be, you can, in your head, you can think to discrete valuation ring. Main examples we have in mind are formal power series or p-adic numbers. And then I use the notation K for the field of fractions, which in this case is formal Laurent series and p-adic numbers. Another way of introducing a discrete valuation ring is having the discrete valued field. Okay, it values in integers together with infinity. So when I put bar, I mean infinity added. And then I denote the valuation, discrete valuation by val. Here is or the order of P, and here is divisibility by T in this 2 main example. Okay, should I stay here or move the? have been teaching many years math, are still not used to the.
But you can use both sides, not a problem.
Okay. Okay. Yeah, I start with, so the goal of this talk is to give a combinatorial classification of toric vector bundles over toric variety or toric scheme. The over toric variety is a classical work of Klyachko, which I'll quickly review, and then I'll give the extension for toric schemes. And just recall, you have a vector bundle over a toric variety, and together with the T linearization means the lift of action of torus and toric variety to the vector bundle acting linearly on each fiber. So which for short, we just call it a toric vector bundle, and I usually abbreviate it as TVB, toric vector bundle. So the T linearization is a part of the data. And it can be shown that not every vector bundle can be equipped with the T linearization. But with the ones which have T linearization can be described combinatorially, as I'll explain. And as Klyachko shows, basically the ones which have T linearization are up to fixed points up to isomorphism of action of torus on moduli of all vector bundles over X. So if you pull back by any element in T, which acts here downstairs, pull back your vector bundle by any element of T, you get an isomorphic vector bundle. If that's the case, then this is if and only if the vector bundle can be equipped with a T action or a T linearization. Anybody interested in the subject can start with the first paper. It's very interesting, contains lots of important, I would say maybe not still completely explored ideas. Okay. Then I start with introducing some linear algebra gadgets. It's supposed to be, these gadgets supposed to be higher rank versions of piecewise linear functions on a fan or on a vector space. As we probably know, line bundles or equivariant line bundles on a toric variety are classified by piecewise linear function. Okay, so I'm now kind of switching to some linear algebra, basic algebra terminology. It's straightforward, but just bear with me and please don't get bored. So we have a vector space E is either C to the R. R is the dimension of vector space, but R is for rank of the vector bundle. Or K to the R, which K is the discrete valued field. And I call it the definition. I'm interested in functions W from E to R bar, R with infinity, and usually I'm interested in the integral ones, so it's in Z bar. So we call it a valuation or vector space valuation if it has these simple properties. If again, my use of terminology valuation may not exactly match what the people use in commutative algebra, or I'm not sure if there is a absolute universal agreement on the term valuation. But anyhow, so it only sends something, it gives a value infinity to something only to zero vector. So it's basically non-zero elements to R and zero goes to infinity. And it has non-Archimedean property. And finally, if you multiply with a scalar, it's insensitive to multiplication with a scalar, non-zero scalar. And I make so this another way is this valuation extends the trivial valuation on the field to the vector space. So it's insensitive to the multiplying by a scalar. You can make a variation of this, and if you have a valued field, and just the same two properties. And then the last one, I make it sensitive or extend the non-trivial valuation we have over K. And so if you multiply a vector by a scalar, you add the valuation of the scalar to your vector, your valuation of the vector. And just to distinguish between these two cases, the trivial valuation and non-trivial valued field, I use valuation for trivially valued case and additive norm for the other case. And it turns out that it will be useful for us to have it a little bit extend this and say that is some additive norm of level M for some positive or non-negative real number. If I multiply by a scalar and M times that a scalar comes out, and I call it additive norm of level M. Usual additive norm is level 1, and level 0 additive norm is a usual valuation. So, and then I introduce some notation for a space of all valuations of level M. I call it P tilde M, B inspired by relation with theory of buildings, which I'll not go into, but it can be after modding out by some trivial, some very straightforward relations. This can be thought of as P0 in the valuations, trivially valued case, can be thought of as cone over Tits building of general linear group, and B1 is the Bruhat-Tits building, again after modding out by some obvious relations as Bruhat-Tits building of general linear group. It's useful for us to consider this.
For higher M, is this also a known construction or something new?
I haven't seen it in the literature, but I'm not really good with the literature of this subject. Sorry, your question was that if this construction is new or not?
Or if this has a name or something.
Yeah, I haven't seen a name for it, but it's kind of very natural. People who, I wouldn't say it's our new definition for people in the area, should be something very standard. But I don't know a name for it.
I guess it's also a Bruhat-Tits building, just with a different.
Yes, exactly. It's just a Bruhat-Tits building scale. But in the
different norm on K, like the.
Yeah. If M is non-zero, they are all the same.
Yeah.
Just as 0 and non-zero are different. And the case of a 0, B0, B tilde 0 can be considered in some way as limit of the non-zero ones, or the infinity or the boundary of non-zero ones in some sense. The same way you compactify Rn to a sphere and add a boundary. Or a disk, I meant the boundary is a sphere. Okay. And again, all level M additive norms. And I use the notation B tilde to be all of them, union of all. And then just to give you a better idea what this big object is. Now time to move to the other side. Okay, first, if you have a omega level 0 evaluation, your additive norm and in integral or integer. Integral, I mean, has values in integers. Then it's very easy to see that it's determined by the subspaces, where for every I you have a sequence of subspaces. If you fix some integer and look at all vectors who have a valuation bigger than I, bigger than or equal to I, it's a vector subspace of E. And if you know it for every I, it's clearly so if it is it's a Z filtration. It's a decreasing Z filtration. As you increase I, the subspace becomes smaller. This decreasing Z filtration is the same data as a W. So and then if it's not integral, then you need to know it for all real numbers. Something very simple. So that's kind of, you can think of this space as all filtration. Integer Z filtration or R filtration decreasing. That's the language Klyashko uses in his classification, and soon we'll get to that. I'm using language of valuation because it's just shorter to say things. Another case is level M, so M equal to 0, another M equal to 1, and so additive norm of level 1 and integral integer values. It's, if you look at all the vectors who have valuation or additive norm bigger than some integer, this is not because of this valuation of a scalar comes out. This is not a vector subspace, but rather an O module. O, the discrete valuation, is everybody who has positive or non-negative evaluation. So it's an O module, and it's easy to see it's a full rank O module in E. It's R-dimensional vector space over our valued field. Okay, and it's easy to see that if you know one of them, one of these guys, you know all of them. So the data of, say, W bigger than or equal to 0 is enough to know the other one. Rest you get by multiplying by correct power of uniformizer. So, and O module or O submodule full rank is usually called the lattice in the literature. And so an integer level 1 additive norm is the data of an lattice or O lattice. In these papers, which we wrote with Chris and Boris, interestingly, we had to use 3 notions of lattice, and everything in terms of terminology becomes confusing. People in the theory of buildings and affine Grassmannian representation theory use lattice in that sense. In Toric varieties, there is co-character lattice and character lattice, which is completely different. Lattice of characters. And there is another lattice in combinatorics, meet, join lattice, that also somehow comes into play. So, but for this talk, that's what I mean. I would say O lattice to emphasize that's full full rank submodule in K to the R, and it's always a copy of, it has a basis by general abstract algebra theorems of modules over a PID, blah, blah. So it's always such a lattice, which sometimes I denote by lambda. Is there exists a basis for the vector space such that this lambda is spanned by this basis, or always has a basis. Okay. So that's how you can think of a space of Z filtrations, or in that 0 case, the level 1 case, as a space of O lattices. O lattices, for people, some people may be familiar with this as a space or collection of or set of all O lattices. Usually it's called affine Grassmannian in the case of general linear group. plays important role in representation theory. Okay. And then one more thing, Z filtration is also data of, it's also obvious that the data of a Z filtration, if you have a decreasing Z filtration of subspaces in a finite dimensional vector space, you can just look at the places that the filtration jumps down or goes down, and you get a flag, or goes up, you get a flag of subspaces. So it's the information of a flag or partial flag. But you have to also record at what index in your filtration, which I it drops. So you have to record the number, which is basically the I in that picture. So Fk is all subspace of everybody has valuation Ck or bigger. This is the minimum valuation possible, and maximum valuation possible is infinity, which is only attained at 0. So another way of describing integer valuations is a space of flags, all partial flags labeled by decreasing integers. Or actually, this could be any real numbers, then you get any valuation, real valued valuation. Okay, so now I have to pull this down, move that up. Okay. Now we come to classification of toric vector bundles. So Kliatchev's classification. I think I have said everything I wanted. No, sorry. Before that, one more thing, which is absolutely necessary. For a basis B, okay, have a basis B in E. I usually write as B1, BR. Vector space basis. I can distinguish choice of a basis B distinguishes a subset of a space of valuations or additive norms. And that's borrowing terminology from theory of building. We call it an apartment. For apartment. Again, this could be 0 or 1, or all of them for every M. If it's 0, it's a Tits building. If it's 1, it's Bruhat-Tits building. And I made, and then if I consider union of all of them, I made up the word total building, but that's just my own made up word. Okay, so what's the definition? So you say that evaluation or additive norm is adapted to a basis B if its values can be obtained from values on the basis elements. So if you have any vector S by X, write it in that basis with a scalar, and then if it obeys this formula, minimum of valuation of the scalar plus valuation of the basis element. If it's valuation so trivially valued, then you do not have this, and then you have to assume that lambda I is not 0. So this minimum of valuation of BI, which appear in your writing your vector with non-zero scalar. If it's trivial, non-trivially valued, then you just have valuation of that scalar. And it's clear that if you have some valuation or additive norm adapted to a basis B, then it's uniquely determined by values on the basis element. So this can be, you can see that it can be identified by sending W to the values of the basis element, R to the R. Okay, so these are, for every choice of a basis, these are copies of R to the R. If if you have a level 0 or a valuation, trivially valued valuation, and then you multiply your basis elements with some scalar, fixed scalars, this apartment consisting of all adapted to B doesn't change exactly, and then the map which sends W B1 BR remains the same. This isomorphism or identification remains the same. But if in the non-trivially valued case, a level 1 case, if you multiply the B's with some scalars, then this map still is identification by R to the R, but the values of the scalars are, valuation of scalars are added here. So this identification is shifted by adding some scalars. So this apartment, again, in the case of M equals to 0, you have two distinguished cases. This is a real vector space. An R-dimensional affine space. Affine space means a real affine space. It means that it's a vector space without a specified origin. So if M is 0, you have a copy of Euclidean space, a vector space, R-dimensional is the apartment. If R is M or level is 1, you have a space R to the R, but without a specified origin. If you, yeah, I hope that explanation clear. So, and that's affine space is related with the term affine Grassmannian used in the literature. That's kind of the reason it's made up of affine spaces. Okay. Now, I guess time to erase something. Yeah. It's okay if I think that's going to work. So this B tilde 0 is a union of infinitely many copies of R-dimensional vector spaces which overlapping on some certain subspaces, and the other one, B tilde 1, is similar, but the identifications or overlapping of these affine spaces are different. It's a lot of interesting combinatorics is in there, which I think for purposes of time, I skip. So now Pliatko's classification. So I'll state it in a not yeah, I'll state it this way. So category of Toric vector bundles over X sigma, so sigma fixed, and in vector space NR of co-characters of torus, the T is equivalent to category. I'll not talk about morphisms in this category, but they are what they should be done. It's very natural category of piecewise linear maps. That definition I have to make. Category of Toric vector bundles fairly E. From the support of the fan, union of all cones in the fan. B tilde 0 or all level 0 additive norms or all valuations. piecewise linear and integral map to send lattice point to lattice point. Okay, so what I have to explain is about the piecewise linear map to this B tilde guy. And actually, that's a kind of a nice generalization of the piecewise linear map on a fan to just real number. These guys just real numbers, piecewise linear maps, classify line bundles. To classify vector bundles, you have to replace this guy with some big object which has the spirit or is a kind of a building.
And E is C to the R or K to the R.
Yes, sorry. Thank you for reminding me. I didn't say what E exactly specified. So in the toric variety, I have the open orbit, and to identify the open orbit with the torus itself, I fix a point which you can think of as the identity in the torus. So that I have already fixed in the toric variety. That's part of the data, obvious part of the data. And then this E is the fiber over this distinguished point, which if you fix a basis, you can identify it with the T to the R or your fields to the R. So that's
something doesn't quite add up. I mean, you want the second category to be independent of the first one, right?
Okay.
So you can't just use the E from the first category in the second one somehow.
So,
I mean, what you're describing is a map or something, or a function.
yeah, so it's a equivalence of categories.
We want the second category to be defined independently of the first. That's why
I guess you need to fix the rank. E is the first category.
You want to sort of say that E is C to the R and then done, right?
Yes.
Okay.
Yes.
Okay.
Yeah, rank is fixed.
So E can vary.
Sorry?
I guess it depends on how you want to phrase it. Right?
Yeah, I think it's a matter of phrasing it.
If you want to talk about category, then E needs to be able to change. Right? So you can have a map of vector bundles.
Yes.
E is isomorphic to EX now. That will be true.
Yeah. So sorry. Rank is not fixed. If you rank is not fixed, you allow E to change.
I think I'm complaining about something much more basic. This might be a notation issue. I'm just saying you want the second category to be somehow independently defined of the first, and right now you're not doing that.
So piecewise linear map for all E.
For arbitrary vector space.
Yes.
Right away. Okay.
For all finite dimensional.
Okay, great. Thanks.
And then I have to just define what a piecewise linear map in this sense is. Definition. Piecewise linear map. This language of Kolyachkov's state, this language I'm presenting is me and Chris's formulation of Kolyachkov's data. In his paper, instead of piecewise linear map, he talks about compatible families of filtration. It's the same thing, just a different way of saying it. But if you look at Kolyachkov's and don't see the term piecewise linear map, don't be surprised. Okay, so piecewise linear map, who is B tilde E, is so the definition is that for every, or the condition is that for every cone in the fan, you should be able to find an apartment, which means a basis, which depends on the cone. Basis. Such, and then of course to this basis there corresponds a subset called apartment, which is a copy of, is a vector space, R-dimensional real vector space, such that, so that's the condition for map phi to be piecewise linear. It is a space of all valuations. So should send this cone to a single apartment. This apartment may not be unique. You may have several choices of bases or apartments, but nevertheless, there should be one, at least for every sigma, there should be one apartment. And this this lives in a linear space, of course. This is a linear space. So this should be a linear map. So restriction to each, the cone should be go to an apartment and should be linear. And we call it an integral, so there is only one condition. We call it integral linear if it's since lattice points in the cone to lattice points here. Integral valuation, of course, makes sense. So we can also have notion of integral linear map, integral piecewise linear map. You can easily see that it obviously extends the usual notion of a real valued piecewise linear map on a fan. And Klyashkov's theorem says that this state of piecewise linear map to this space of valuations in integral piecewise linear map are exactly the classified toric vector bundles up to equivariant of isomorphic.
Sorry, one small question. The compatibility condition is encoded in the file.
Compatibility, Klyashkov's so-called compatibility condition is this linearity of the. He doesn't talk about all valuation. He talks about Z filtrations, and then to each ray in the fan, he assigns Z filtration, which in our language is a integer valuation, integral valuation, and the filtrations coming from rays of the same cone sigma should be related or compatible in some linear way. And it just translates immediately. It just means that you have a linear map from this cone to this apartment. Okay. One may ask why. What's the use? Why would you? What's the advantage of just thinking of valuations and then realizing that it's related to the theory of buildings? Okay. As far as Klyashkov's classification may be concerned, it's just makes things just shorter to say, not much more, but it has some, at least for us, interesting applications. There are buildings for any linear algebraic groups, and then one can use them to define same piecewise linear map to other buildings, and they give classification of toric principal bundles instead of vector bundles. Just more or less immediately gives us the gadget that classifies toric principal bundles over toric varieties. Another thing is that there is a relative version of building, which we talked about, Afghan-Grassmannian, or at B tilde 1 with additive norms. That's also a building. And turns out that they classify toric vector bundles over a DVR. This, again, just point of view of buildings just tells us that just immediately gives us the right gadget to classify a lot of different things. Just provides an immediate way of recovering what gadgets classify, might be correct gadgets to classify other things. Okay. Now I talk about classification over DVR. I have time to say, before I go into that, maybe I'm tempted to say one word about equivariant chain classes. Chain classes are understanding chain classes or describing chain classes of toric vector bundles is in the Klyashkov's paper. The equivariant chain classes following Klyashkov's compatible filtration language is in, I know it from Sam Payne's paper, moduli of toric vector bundles. But again, this look provides another quick way of packaging all the data and reading of equivariant chain classes of E. So it's not difficult to construct universal maps, which are basically come from elementary symmetric functions. So for every integer I from 1 to n is the dimension. R is the rank. So you have elementary symmetric function and R elements, but this gives a function is easy to construct a universal function on all Z filtrations for all labeled flags or all valuations over E to R. It's actually pretty like, I'm afraid I erased it. No, I haven't. Anyhow, I wanted to bring up the labeled flags. If you have think of evaluation as a labeled flag, you have your labels, K of them, to basically consider elementary symmetric functions in your labels or values of valuation. Each label repeated as many times as dimension of the flag minus the previous one. And now you can easily construct using elementary symmetric functions, universal functions on the space of valuations. And the equivalent chain class of your vector bundle is just piecewise polynomial function obtained by composing your piecewise linear map with this universal function, elementary symmetric function. So you get this. This is a piecewise linear composed with elementary symmetric function, is a piecewise polynomial function on the fan, easy to see. And that's exactly representing the equivariant chain class. Sorry, I said it fast, but just want to say that this contains immediately data of chain class.
And do you define this apartment by apartment? Note that it gives the same thing if you take an automorphism from one apartment to the other? Or?
Oh, yes. It's not difficult to check that. If you go from one apartment to apartment, it's well defined.
Okay.
So in function, we capture the T action also on the E. And when you take TI, T action on the bundle also is captured in the CI.
Yes, that's the equivariant chain class. Equivariant. Okay, and now about Toric scheme. I have set up all the gadgets, so hopefully this part will be kind of quick. So now we take things over DVR. K is the field of fractions or discrete valued field. And then we have a T is a split torus over O X on your scheme over O with usual conditions, irreducible, normal, finite type, and such that I also have to mention that a spec of O has 2 points. One corresponds to the prime ideal 0, the other corresponds to the unique maximal ideal M generated by the uniformizer. The point corresponding to this, usually called a special point. For S, I write S, and then this one following Mumford and others call it eta. So generic point, a special point. In the usually in the especially with the intuition of thinking of power series ring, to think of this as T equal to 0, a special point, and the generic point is T not equal to 0, and a spec O is just the infinitesimal neighborhood of origin in the affine line, and then any scheme over that, you think of it as some one parameter degeneration or infinitesimal degeneration of a variety over K. A variety over K, if it's defined over O, or an O model of it is basically infinitesimal degeneration of fiber over eta to fiber over S, a special one. So you can think of this schemes over O as infinitesimal degenerations of varieties over complex numbers or over your field. Okay, and this is a Toric toric scheme is same definition as a toric variety, but you have torus, generic torus, fiber of torus over K, or over the generic point. It comes with the data of an open embedding, and such that the action of torus over O extends the usual action of this torus. Is basically a copy of torus over the field of fractions on itself. Okay, and so that's a formal definition. I think goes back to the early book of Kempf, Mumford, others on toroidal embeddings. Last chapter you can find this, and then the classification, which is kind of a straightforward and it's not that difficult to see, is that toric schemes over a DVR are classified the theorem, Mumford and others, the toric schemes are classified by fans sitting in the co-character lattice for us, positive or non-negative real numbers. Oops, sorry. So I think of this as NR, and then this direction as positive numbers, and then you have a fan here. The fan, which intersection of this fan sigma with the NR or level 0 gives you the fan of the generic fiber, which is a usual toric variety over K, or if you specialize T to some non-zero number, a toric variety over complex numbers. But there is more data here which tells you how this toric variety degenerates as T goes to 0, and it can be a non-irreducible. It can have several irreducible components. So the generic fiber is a toric variety. Special fiber is a union of toric variety for the action of a residue torus or residue field of your DVR. Okay, and it's encoded in this fan, or the cones that do not lie in level 0, which can be also understood as intersection with level 0, and then it becomes a polyhedral complex. So it's a data of a polyhedral complex and its recession fan, which is the limit at infinity. Okay, so these toric schemes are encoded by this kind of piecewise linear or polyhedral data. And finally, I can now state the classification of toric vector bundle. Definition of toric vector bundle over a toric scheme is the same. So a vector bundle over a scheme, such a scheme with lift of action of T. Or you have this one parameter family, infinitesimal degeneration, and over that you have a vector bundle which also degenerates. So just have to define notion of, and this notation might be useful. So this fan in NR cross R positive, the intersection with level 0, which is a fan, usual fan, call it sigma 0, intersection with level 1, last coordinate 1, I call it sigma 1. And then the whole thing is sigma. So sigma 1 is a polyhedral complex, sigma 0 is a fan. Okay. Then we have definition of more or less same definition of piecewise linear function map from this fan which lives in one more dimensional space. So this total building, if I recall you, is the level 0 ones and level 1 and everything valuations. And then as before, E is the fiber over is the fiber over generic torus, which we think of it as open or orbit. or it's the identity of the torus. And then E is the fiber over this distinguished point, which can identify with the R, K to the R. K is the field. Okay, so what is a piecewise linear map? Same definition. For every sigma, there exists the basis. Exactly same definition, such that phi from sigma the total apartment is linear. This guy, because it's union of all of them, now is a copy of R to the R cross R positive. And there is one more thing I have to impose, which is also very, very natural, has to be like that. This guy has this one, you have an extra coordinate R positive, and so this lives in a kind of graded, has a grading, and this is also this positive grading. So this map should respect grading.
Yeah, but then your frames have to be, there has to be exact there, right?
Okay. And of course, everything should be, for classification, I want to be integrals, and lattice points to lattice points.
I'm just confused. If you take this union, then you only get Z grading equal to 0 on the right hand side of that.
Sorry, can you? It's basically, it's determined by its restriction. It's basically that phi map is determined by restriction to sigma 1.
Okay.
I think the confusion might be that is M an integer or a real number?
Exactly. Yeah. I think technically it's an integer, and so it's Z here, but then you can also take it to be a real number, and then this is fine.
Yeah, I'm taking it to be a real number.
I see. Okay.
And in the previous definition, it was real number. But really, back of our mind, we only care about the level M points. Level M points. So preserve the grading. Level M points, these are additive norms of level M here, level M. So, and then theorem Boris's last name is pretty long. Right, that's the T. Default-key. So the toric vector bundles over discrete valuation ring O are classified again as in the sense of equivalence of categories by integer piecewise linear map phi as defined. I can, instead of introducing this B tilde M, etc., I could just work with B tilde 1. There is a little technical point of why not doing that. Strictly speaking, if you have a fan which is not complete, does not cover this whole half the space, then its recession cone of this may not be a fan, strictly speaking, and so that causes a little bit problem. But if it's a complete fan and then you have a complete polyhedral complex here, then I could just, which means the scheme is proper, then I could just think of maps from sigma 1 to the Bruhat-Tits building or B tilde 1. And instead of this definition, I could define the version of it that this is a piecewise affine map from sigma 1 to B tilde 1. And think of it as a piecewise affine map. Anyhow, either whichever way you prefer to formulate it. And then, okay. I'm basically done. It depends. Do I have if people are interested to hear 5 more minutes of some interest or not. Okay. So one of the very interesting Kolyachko's statement, I like it very much, is which he proves this linear algebra statement to address the problem of splitting of a toric vector bundle. Sorry, I'll not do justice to this subject. If you are interested, you can read it more in this paper and other papers, which means when this is equivariantly isomorphic to a sum of line bundles, for some reasons, as motivations, I think coming from representation theory and Horn's conjecture, I think he was interested in this kind of question. And then it's very simple to, not very simple, it's kind of a straightforward to see that E is a split. It decomposes into direct sum of line bundles if and only if phi image of this piecewise linear map lands in one apartment. So there exists a basis, all these valuations or Z filtrations are adapted in that way to that basis. And so the way this theorem works, this criterion is exactly true in the case of DVR as well. So we have same criterion for a splitting. It is not difficult to see that it implies that all toric vector bundles over E1 over complex numbers are a split. That's the linear algebra exercise. It's not, again, I'm out of time. I don't have time to explain the example, but this classification gives a way to construct many that are not true in the P1 over this split valuation ring. And the linear algebra problem I was going to state is the following. So Kolyachko proved this theorem that all rank are toric vector bundles over En a split if the rank is small. If the rank is at most n-1. And to do that, he proves this statement in linear algebra. Now you can forget about everything, you need to know first year linear algebra. Okay. So you take this finite subset of vector subspaces of C to the R, or any field, over any field, I like C. Okay. And suppose of R-dimensional vector space. Suppose this condition holds for every collection, sub-collection of these subspaces, any arbitrary subspace, set of subspaces. For any sub-collection which has R+1 element, they are all spanned by same basis or subsets of the same basis. So there exists a basis depending on that R+1 element subset that expands basis, expands all subspaces in R. So any collection of R+1 subspaces you pick from this 1 billion many subspaces, you can find one basis that expands this R+1 many subspaces. Subsets of that basis expands that. Then this implies that all subspaces in S are expanded by same basis. Sorry, I'm in the corner of the board. So if R+1 have this property, all of them have this property. This is reminiscent of Helly's theorem from convex geometry. Polyachko calls it Helly's theorem, Helly type theorem. I realized with my student that Xiao Yu Huang, that this statement makes sense for any building. And then we pose the problem of finding this number R+1. What is the analog of that for other buildings? Haven't succeeded in finding it for other buildings yet. And Boris Lichovsky proved it, same statement, instead of subspaces, he proved it for all lattices in a valued field for affine Grassmannian, so which implies Polyachko's statement for projective space over a discrete valuation. Thank you.